Hello and welcome to my 2212 Lab 4 Circuits. In this lab, we will be discussing various aspects of circuit systems, including but not limited to modeling a circuit system computationally, predicting current at different points in a circuit, utilizing the charge conservation principle, studying the relationship between voltage, current, and resistance, investigating RC currents in which a resistor and a capacitor are present, and calculating a RC constant. The first circuit modeled is a simple circuit consisting of two batteries of 1.5 volts, two resistors, one at 47 ohms and one at 100 ohms, and two ammeters to measure the current at two different places. Because of the node rule, we're able to conclude that I1 equals I2, and through this and the summation of potential difference in the entire circuit being equal to 0, we're able to predict the current at each location being 0.02 amps. That simple system was shown on the computational model of circuits, and the measured current was 0.02 amps. This proves that our predictions were correct, that the current is predictable. By reversing the ammeter, it is noted that the current is still 0.02 amps. This is because no matter which direction the current flows through the ammeter, it will read it at the same value. Next, with this simple system, I utilized a voltmeter to measure the potential difference of the two sections of the system. The voltage measured 3 volts, which is to be expected given the two 1.5 volt batteries present in the system. The voltage between different sections of the system were measured and are on the table to the left and graphed on the right. You can note that the system reached the maximum of 3 voltage of the batteries and then went down as each resistor was met. Something to note is that if you add the change in voltage across the system, it will equal 0. This shows the conservation of charge principle. Next, an ammeter was placed in parallel with the 100 ohm resistor. You can note that the current went up as the current went around the resistor through the path of least resistance through the ammeter, and therefore it was not reduced to a lower current. This can also be shown by the fact that the change in voltage is 0 between the 2 points, showing that no resistor was met. With the voltage calculated earlier and the measured current, we can calculate the resistance of each resistor and the wire. Note that the wire and ammeter have 0 resistance. This is because it is an ideal case. The next system analyzed was an RC circuit in which a resistor and a capacitor are present. In this case, the light bulb is the resistor. A 10 ohm light bulb took 20 seconds to charge and 20 seconds to discharge, and a 20 ohm light took 40 seconds to charge and 40 seconds to discharge. It is worth noting that when the battery is put in, the light bulb starts out very bright and slowly dims as the capacitor gains charge and the current decreases in the system. The opposite is seen when the system discharges the capacitor, in which the current starts high and decreases. The next system analyzed was an RC circuit with a 9 volt battery present, a 30 ohm light bulb present, which will act as the resistor in this system, a 200 millifarad capacitor is present, in addition to an ammeter and wire to close the circuit. Because of the charging and discharging of the capacitor, time is now playing a role in the voltage across the capacitor. This voltage can be measured every second for 20 seconds and analyzed in order to find the RC constant of the capacitor. We're able to calculate the RC number of the capacitor through the conservation of charge principle, in which we sum the change in voltage of the system and equal it to 0. Through rearrangement of the change in voltage of the capacitor and change in voltage of the resistor, we're able to find the relationship that the natural log of the change in voltage over the change in voltage original is equal to the minus t being time over RC being the RC number. Through the linearization of this plot, we're able to go and take the slope being the 1 over RC number, and we are able to calculate the RC number being equal to 6. The results of this lab lead us to further questions. The first being that if we were to do this lab in real life and use an actual ammeter instead of an ideal simulated ammeter, what would the difference be? The difference would be that the ammeter would be imperfect, and therefore it would cause resistance to the current, and therefore the true current would be larger than the measured current. The second question, which is, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistors in the circuit? How quickly would our model predict the capacitor to reach full charge? The ideal model would predict the capacitor to reach full charge sooner than it would happen in real life. This is due to the wires having resistance in real life and not in the ideal case. However, our model would realistically prove to be close to the actual result, as the resistance in the wires would be very little.